Hey everyone, I hope that you had a great break. I'm sorry I can't be there with you today. Today we're going to learn about 6.4, separation of variables. This is a specific type of a differential equation that can only solve certain differential equations, but it's a very simple way that uses a lot of anti-differentiation techniques we've been talking about. So let's first talk about what a separable differential equation is. So if you have a separable differential equation, you have dy dx. Remember, we're given the derivative. We're going to have to integrate to solve it. So you have dy dx equals f of x times g of y. So we have some product of functions. One has to do with x, one has to do with y, and it's called separable because, surprise, you can separate them. So what I could do is I could move the dx over to the right and put the g of y underneath the dy. So I would have dy divided by g of y is equal to f of x dx. And then I could integrate both sides, and you would have to remember a plus c on one side, because you get a plus c on both sides. But I mean, if you have, like, let's say that you solve this somehow and you end up with, I don't know, 2y plus 1 plus c is equal to negative x plus c, something like that. Well, if I just move I mean, the constants are different, so I should probably label them. But if I move the c to the other side, I would have c2 minus c1, which is just another constant. So usually we just do the y, usually we leave without a c, and then we just do the x side plus c, something like that. So some examples of some separable differential equations you might see. You might see something like this. So you might see dy dx is equal to something simple like just xy. So if it was xy, that's certainly a product of functions. I could divide both sides by y, multiply both sides by dx, and integrate to solve. Another thing you might see is like something like x over y. So y prime, remember, is the same thing as dy dx. Could see x over y. Now that's still a product of functions because it's x times 1 over y, right? So I could, this time I would multiply both sides by y. I would have y dy is equal to x dx. We're going to see one similar to that a little later. And integrating both sides of that is very easy. You also could see something like dy dx. I'll put it over here. You could see dy dx is equal to x times y plus 1. Now, sometimes they're sneaky with one like this. They could write it with the x distributed, xy plus x. So that doesn't immediately look like something separable because it doesn't look like a product of functions, but if you factor out the x, you're going to end up with this guy right here, which is definitely separable. So those are the kind of functions we're going to be looking for, and usually they also give us an initial condition so that we can solve for that c. So without further ado, let's take a look at a separable differential equation that we can solve. So here we have, this is the first example on your gold sheet, and you might want to follow along with me. So if you don't have the gold sheet, make sure you ask for that from the sub. So we have xy squared. I'm going to distribute that square into x and y, because remember that's xy times xy, and so I could have this as dy dx is equal to x squared y squared. That's certainly a product of functions, so I can separate it. So I'm going to divide both sides by y squared and multiply both sides by dx. So I'll have dy over y squared. You could write that as 1 over y squared dy, however you want to, is equal to x squared dx. So we have now separated the variables. Now, AP always gives a full point for doing that separation. All you have to do is move the y's to one side and the x's to the other. And notice on your gold sheet, that's the first step, is to move the x's and dx's to one side and y dy's to the other side of the integral, or of the equal sign, excuse me. Now we're going to integrate both sides. And it's weird because we haven't really done a lot of integration with y. It works just like the x. So let's think about this. We're integrating on the left. We're doing y to the negative 2 dy is equal to the integral of x squared dx. So now I'm looking for antiderivatives, and this is number 1 on the original gold sheet that we had that had all the big 15. So I'm just going to add 1 and divide by the same. So if I add 1 to negative 2, that would be y to the negative 1. And then divided by negative 1, I'm just going to put a negative in front to show that. If I took the derivative of this, it would give me y to the negative 2. And that'll be equal to 1/3 x cubed, and then we need our plus c. And we're just going to put it on the right because the two c's have combined to create that c. So now, the third step that you'll see is to find c. There are some cases actually where it's easier to solve for y first. In this case, we will find c right now. And you can do it either way. So we have a negative 1 over y is equal to 1/3 x cubed plus c. So now I look at my initial condition to solve for c. And I see that f of 1 equals 1. So when x is 1, y is 1. So I have negative 1 over 1 is equal to 1/3 times 1 cubed plus c. That's a little overkill, right? I wouldn't have had to put the 1 cubed there, and this is negative 1, but I just want to go through the process each time. So I have negative 1 equal to 1/3 plus c. So if negative 1 is equal to 1/3 plus c, I can subtract 1/3 from both sides. Negative 1 is negative 3/3 minus another third is negative 4/3 is equal to c. So now what I have to do is I want to solve this equation for y. That's our last step, and we have to make sure it's a function. So we have to make sure we don't violate any vertical line test rules or anything like that. So we're going to go back to our function up here, and we're going to put in our c values. So right now I have negative 1 over y is equal to 1/3 x cubed, and that looks like minus 4/3 is our c. And now what I want to do is get this to be solved for y. Right now I have this negative 1 over y. This is like an implicitly defined function. I want to get it to be explicit, so y equals. So I'm going to dress this up a little bit. I have the same denominator over here on both of these fractions, so I could write negative 1 over y is equal to x cubed minus 4 over 3. Now if I multiply both sides by negative 1, I'll have 1 over y equals negative x cubed minus 4 over 3. And then some people talk about cross multiplying here. We can just take the reciprocal of both sides. That's fine. So we have y equals negative 3 over x cubed minus 4. And there's our answer. Now, we talked a little bit about the domain of differential equations. And so what I want to do right now is take a look at the slope field for this. And this is actually an application. So we got this function right here, negative 3 over x cubed minus 4. There's an application that I put on your Moodle page. Let's take a look at that right now. It's this Desmos slope field generator right here. And Desmos is an awesome graphing function that I've used a couple times with you guys, but not a whole lot. But if you click on that, it gives you this generator, and your slope field is going to look different when you start, but you can type in anything you want here. So I chose xy squared, which is exactly the differential equation that we just solved. So we have xy squared. And let's take a look at what that slope field looks like. A little weird slope field. It doesn't. This generator will give you a slope field from negative 10 to 10 for any differential equation that you choose. But it looks like there's some spots missing, and I think it's just because they get so steep at this point that they'd be vertical. But what I'm going to do is I'm going to graph the function that they gave us. So we see that the function that they gave us goes through our initial condition, 1, 1, which is really nice. That's one thing I like. If you have the function like selected like this, it shows the intercepts, it shows any maximum or minimum values, and it also shows any grid point it goes through. And that's really nice for an initial condition problem. So we see it goes through our condition 1, 1. But the problem is, we talked about, when we first talked about differential equations at the beginning of chapter 6, we said they can't be in like two different places. And you see this goes over a vertical asymptote. So we kind of have to choose the left side or the right side. And if you think about it, we want it to go through our initial condition. So it should be the left side. And now we just have to figure out, okay, so what's our domain? Where does it stop? Well, if you look at the equation, if you look at the function, we have 3 over x cubed minus 4. That vertical asymptote is going to happen when the denominator is 0. So I'm going to go back to my PowerPoint, and we're going to get a domain for this function. There we go. So we don't want the bottom to be 0, so we can't have, I've got to make my slideshow here. So we can't have x cubed minus 4 cannot be equal to 0. So that means x cubed can't be negative or positive 4, which means x cubed can't be, or sorry, x can't be equal to cube root of 4. So that must be where that vertical asymptote happened. And because we want our initial condition, f of 1 equals 1, to be on the graph, we need it to be less than cube root of 4. So our domain for this is going to be from negative infinity all the way up to the cube root of 4. Yeah. And that is the solution to our differential equation. So let's take a look at domain just in a little bit more detail. Change back to a less offensive color here. Let's do green. So if we think about our domain, there are a few things that we want to focus on. We need to avoid any discontinuities. Avoid discontinuities. And we had those few different kinds of discontinuities we talked about at the beginning of the year. The ones you'll see most often are 0 in the denominator, and that would be a vertical asymptote. That'd be a vertical asymptote. Another thing that you'll see a lot is if you take the natural log of 0, that can't happen, or the natural log of a negative number. That can't happen either. So those are spots where we're going to have a discontinuity. Another thing that you don't want to do is take the square root of a negative number. That would be bad news. And what all of this gives you is it's going to give you intervals. So like for the last one, if I had made a number line, our only problem spot was the cube root of 4. That was the only problem spot we had because that was our vertical asymptote. And then what I just had to do was say, okay, which side do I want? Which side of cube root of 4 do I want? Do I want negative infinity to cube root of 4 or cube root of 4 to infinity? So those are called the intervals of validity. Intervals of validity. So if you find, like, let's say that you solve a differential equation for some reason, and it ends up being 1 over x squared minus 25. So you should be able to see here that the problem spots are at 5 and negative 5. So negative 5 and 5 are our two issues. And let's say that the initial condition they give us is that f of, let's say, negative 6 is equal to, what would that be? 36 minus 25 is 11. So that'd be 1/11. Okay, well, we need that initial condition to be on our graph. It wouldn't make much sense if, like, it was between negative 5 and 5, but negative 6 was our initial condition. So here we have three choices for an interval. It could be negative infinity to negative 5, negative 5 to 5, or 5 to infinity. Because we're given this negative 6, negative infinity up to negative 5 is going to be our winner. Okay, one other thing that you should note is that AP will always ask for this explicitly. You'll be asked explicitly for the domain. If they don't ask you for the domain, you don't have to give it. Okay, but sometimes they say include the domain in your analysis of this differential equation. So in this case, if they said include the domain, you would have to say it goes from negative infinity to negative 5. The graph of this would look something like this. So you don't care about any of this. You only want this little swoosh over on the left, because we don't know what happens. Like in real life, it might only follow this curve, and none of that will matter anymore. Cool. So let's try another example. Ooh, if it'll let me change, there we go. So once again, we're given an initial condition. When x is 1, y is 2. And this differential equation, y squared over x. So let's do this one together as well. So this one's not on your gold sheet. You'll want to do this in your notebook. So we're going to separate our variables. So if I divide both sides by y squared, I'll have dy over y squared is equal to 1 over x dx, or dx over x, however you want to do that. We'll integrate both sides. So on the left, I have integral of y to the negative 2 dy. On the right, it's integral of 1 over x dx. The left side, that's going to be negative y to the negative 1 again. We just did that on our last example. That'll be equal to the natural log of absolute value of x, and then, of course, plus c. So this is negative 1 over y is equal to natural log absolute x plus c. And let's plug in our initial condition to try to solve for c. So we'll solve for c again in this situation. We could take the reciprocal and then solve for c, but we'll just do it right now where it is. So we have negative 1 over y, that's negative 1/2, oops, is equal to natural log of absolute x, which is 1, plus c. Well, natural log of 1, we should know that that's 0, right? Because the question is e to what power gives us 1, and that answer is 0. So I have negative 1/2 equals c. So then our explicit, we have negative 1 over y equal to natural log absolute x, and then plus c is going to be a minus 1/2, because we just found our negative 1/2 for c. And then I can take the reciprocal, so I have negative y equal to 1 over natural log absolute x minus 1/2. And then I'll take the negative of both sides. And the negative, remember, you can apply anywhere. I'm going to apply it to the bottom. So I'm going to have y equals 1 over 1/2 minus ln absolute x. Now, the absolute value in here right away should give away an issue, because that means that we could have a negative x or a positive x, but we have lots of places here where we're going to have an issue with an interval. So if I, let's see here, if I think about where I'm going to have issues here, for sure x can't be 0. So I'm going to put on my number line all the issue places. X can't be 0, because you can't take the natural log of 0. I also can't have the denominator equal to 0. So 1/2 minus ln absolute x can't be equal to 0. So if we add ln x to both sides, we have ln absolute x can't be equal to 1/2. So that means if we exponentiate here, if we bring the e to the other side, then we have absolute x can't be equal to e to the 1/2, and that's root e. So it can't be equal to root e. And the absolute means it can't be plus or minus. So x can't be equal to plus or minus square root of e. So those are other issues. So negative root e and positive root e. So we have three possible intervals. Could be negative infinity to negative root e, could be negative root e to 0, 0 to root e, or root e to infinity. So let's take a look at our initial condition. Well, 1 has to be our x value. 1 lies between 0 and root e because e is 2.7 something, so the square root of e is going to have to be more than 1. So that's the interval that we want. So the domain for this guy is going to be 0 to the square root of e. That's our domain. Okay, and this is our solution. So let's take a look. And one note before I move on, sorry, I want to take a look at the slope field of this, but between 0 and e, all of those numbers are positive. So sometimes you'll see solutions that won't have this absolute value there, and you think, well, I thought I had to have the absolute value there. Well, 0 to e is all positive, so we don't have to worry about the absolute. So you could just take those away. Let's just do that and see what happens. There we go. So we could write it like this, as long as you include the domain. That's really important. So let's take a look at the slope field for this. Got it right here. So here's our equation that we just did. Y squared over x is our differential equation. So it looks like we might have a horizontal asymptote going on, maybe a vertical asymptote. I'm not really sure. Let's turn our function on and see what we end up with. So this is the function we just found. 1 over 1/2 minus natural log of absolute x. And our initial condition, I believe, was 1, 2. There it is right there. So we see where we have our issues. At 0, it looks like we're not differentiable. It looks like there's a cusp there. And also, I think there'd be a hole there because you can't do the natural log of 0. And the part of the equation that we're going to want is just the one from 0 up to this must be the square root of e, where we have this asymptote. So let's see if I can get my keyboard here. And I'm going to put in... I don't know if it'll let me do brackets. Well, I wanted to be able to put in a restriction there. I'll probably do it here. Oh, don't let me do brackets there either. That's too bad. Put on my keyboard for this. So if I only restrict that to being from 0 less than x less than the square root of e, you can see that it gives us that restriction that only focuses on from 0 up to the square root of e. So that would be the graph of our solution, and we see it fits our slope field very nicely. Cool. All right, back to our PowerPoint here. So, moving on to another example. This is another example from the gold sheet. And if you'd like to try this on your own, you can give it a shot. Try separating the variables. This one is pretty straightforward. And solve for the c value. And then just remember to consider which part of the solution do I want. So if you want to give that a shot, go ahead and do that right now. All right, welcome back. Hopefully you were able to give this a shot. Let's try it together now. So I'm going to multiply both sides by y and multiply both sides by dx. So I'll have y dy is equal to negative x dx. Integrate both sides. So it looks like we'll have 1/2 y squared equal to negative 1/2 x squared plus c. So what I'm going to do here, just to kind of make my life a little bit easier, I'm going to multiply both sides by 2. If I multiply both sides by 2, I have y squared equals negative x squared plus c. And now, I multiplied c by 2 as well, but just creates another constant. So I just left it as a plus c. And now let's plug in our initial condition. So we have y equals negative 3 when x equals 4. So negative 3 squared is 9. Is equal to negative 4 squared, which is negative 16, right? Because we square first, then apply the negative, it's order of operations, plus c. So if we add 16 to both sides, it looks like 25 is equal to c. So let's put that in right here. You can put it in any spot that you have a c. So we have y squared is equal to, let's do 25 minus x squared. So now we're going to take the square root of both sides to get y by itself, and of course we need a plus or minus the square root of 25 minus x squared. So you probably see the issue here, that plus or minus, this is a circle, right? We've seen so many semicircles, but this is a circle, and we can only choose one of those. So let's check our initial condition. When x is 4, so 4 squared is 16, 25 minus 16 gives us 9. Square root of 9 is 3. We need it to be negative 3, so I want the negative. So y equals negative square root 25 minus x squared. And that is our particular solution. Now the domain for this, remember a semicircle only is going to go from negative 5 to 5. So the domain, you could say, is from negative 5 to 5. But really what's interesting here is the range. The range goes from negative 5 to 0. And let's take a look at our slope field to see if that's what we end up with. So here I've got the next slope field up and ready to go, negative x over y. We see we have that circular pattern. We can't have the whole circle, it can only be one of them. So I've got my negative plotted here, and let's see if it goes through our initial condition. Our initial condition was y is negative 3 when x is 4, and there's that point right there, 4 comma negative 3. I love this application because it shows all of those grid points that are on there, including our initial condition. Just the bottom half. Cool. All right, another problem here to try. So we got dy dx equals 2xy, and they tell us f of 0 is negative 3. That's our initial condition. So we're going to separate this guy. We'll just use red, that's fine. So I'm going to divide by y and multiply by dx. So I'll have dy over y is equal to 2x dx. Integrate both sides. 1 over y, so that's going to turn into natural log of absolute value of y is equal to, let's see, this would be x squared over 2, so the 2's are going to cancel. So we just have x squared and then plus c. So now this is one where I'm actually going to solve for y first, just to give you a taste of that, and then we'll solve for c after solving for y. So to get rid of a natural log, I'm going to do the snowman bump here. So I'm going to bump the e to the x squared plus c. So we'll have absolute y is equal to e to the power x squared plus c. That whole thing is up in the exponent, right? Because I'm exponentiating the entire side. It's like I took that whole part in parentheses and made that the exponent of e. Now, this is something you see all the time. If you have 1 over y equal to something multiplied by x, you're always going to end up with this e to the x squared plus, or e to some power plus c. So we can use exponent rules. Remember, if you have like, I don't know, 2 cubed times 2 to the 4th, that ends up, you have 3 2's here, 4 2's here, all multiplied together, it'll be 2 to the 7th. That's 4 plus 3, so 2 to the 3 plus 4. I could do that with my e here. I have an addition. I can make it look like this, where it's a multiplication of two different exponents. So I'm going to write that as e to the c multiplied by e to the x squared. Well, e is a number, right? It's 2.7 blah, blah, blah. When I take a number to a constant, it's still a constant. So I could just put a c here instead of e to the c. I'm actually going to put an a there because it's so different, right? We've done so much to this constant. I'm going to write absolute y equals a times e to the x squared. Now, I like to do this because it's a lot easier to find the constant here than it is up here. If you found the constant here, it would have a natural log in it. But in this case, hopefully it'll be a little easier. And I think it's easier because we have y by itself. We just don't have to deal with that natural log. But the absolute value is a little bit tricky because that a could be a positive or a negative constant. So I'm going to write this as y equals plus and minus a e to the x squared. So now let's plug in our initial condition. So we have f of 0 equals 3. So x is 0, y has to be negative 3. Bring that up here. So we have negative 3 equal to a e to the 0 squared, which is just e to the 0. E to the 0 is 1, so negative 3 is our a. So that's one thing you have to be careful with the plus or minus. If I did the absolute of 3, I would have gotten a positive value for a, but you have to make sure that your initial condition works. So a is negative 3, so I have y equals negative 3 e to the x squared, and that is my explicit solution. So think about the domain for this. Well, there's no problems, right? We don't ever have any asymptotes. We don't have any natural logs of 0 or square roots of negative numbers or anything. So this is good for all real numbers, negative infinity to infinity. And let's take a look at the slope field and see what it looks like. Keep, and let's go back over here. All right, so here we have our 2xy. Looks like they kind of look like parabolas, but they're not going to be because we have an e to the power. We turn that on. There is our initial condition, 0, -3, and it will go on forever in both directions. If we scroll a little bit, I don't know if I can scroll. I can. Okay, so it looks like it goes down forever. It'll go left and right forever, but it'll go very, very far down. Okay, cool. So that's our particular solution to this slope field. All right, back to our show. Okay, so let's check that one just for kicks and giggles. Right, we have that -3 e to the x squared, and I'm going to talk about how to be able to check your solution here, because there's a y in our differential equation which we haven't seen a whole lot, and we want to talk about what that's going to look like. So y is equal to this function. So dy dx I can do in two different ways, right? dy dx, I can just take the derivative of my function, right? And if we use chain rule, that's going to be -3. You leave the e to the x squared alone, but then you have to multiply by the derivative of the baby, which is 2x. So altogether, that looks like -6x e to the x squared. Now, this has to be equal to our differential equation. It's got to be equal to 2xy. So the question is that equal to 2xy? Well, we've got an equation for y here, so let's just multiply it out and see. So 2xy will be 2x times -3 e to the x squared. That would give us -6x e to the x squared. And that checks out. So we've found a function whose derivative is 2xy. And that was kind of the goal of finding a particular solution to the differential equation. Nice. Come on. There we go. Okay, I'm going to have you guys try this one on your own. It's not too bad. I think you'll be able to solve it. So just remember, we want to separate our variables. There's no x here, so think about what that means. Talk with the neighbor if you need to, and I'll see you back here in a minute. All right, let's give it a shot together. So if we divide by cosine squared y, we have dy over cosine squared y, and that would be equal to just dx. So we integrate both sides. We've seen this a lot with integration by parts, right? If you have integral dx, we should be able to find that's just x, right? So this is a little sneaky. This is integral of secant squared y. Hey, that's an easy one. Equal to integral dx. So this is just tangent y is equal to x plus c. Now, at this point, if I take the tangent inverse of both sides, it'd be a little messy, so I'm just going to plug in 0 right now for x and y. So I have tan 0 equal to 0 plus c. Tangent of 0, think about our unit circle. Length of the tangent line at 0 is 0, so I have 0 equals c. So that means that tangent y is just equal to x. Take tangent inverse of both sides, we have y equals tan inverse of x, and that should be our particular solution. Domain on this, all real numbers, -infinity to infinity, because you can take the tangent inverse of whatever you want. Let's take a look at the slope field for this, and I think that's going to be it. Keep those. Here we go. Slope field. Where are we? There we are. Okay, let's take a look at that slope field. So we have, it looks like lots of things that kind of look almost logistic, right? And that makes sense for tangent. It should be a whole lot of things that go up, and we have to figure out which one we want. Well, if we look at it, our point 0, 0 should be on there, and there it is. So it's just this one little swoop of arctangent, and that's all there is to it. So, where are we? So, that's all I've got for you. And your homework that I want you to do, this is a little bit different than on the sheet. It's the homework from Friday before break, according to the gold sheet. So everything's shifting just a little bit, and it should be something I mentioned in my email, I hope, about how this homework is changing just a little bit. We just shifted one day. So tomorrow the plan is to do review and to do some AP problems that have to do with separation of variables and slope fields and all this kind of stuff we've been working on, maybe Euler's method. We haven't seen that in a little while. And then on Wednesday, we're going to have our quiz. So there is a quiz Wednesday. Just keep that in mind. All right. If all goes well with my flight, I should see you guys tomorrow. I really look forward to it. I've missed you very much. And very happy holidays to everyone. Happy New Year. And I will see you tomorrow. Have a great one, guys. I love you guys. Bye-bye.